I want to tell you about a paper I published in 1939, because I think almost nobody who watches videos about fast-moving stars near black holes today has ever heard the name attached to the theory that predicted they could exist in the first place. I'm going to tell you what I understood then, what I couldn't have known, and what happened decades after my death that proved the mathematics right in a way even I never got to see. In the years before the war pulled my attention toward weapons physics entirely, I was working, along with a graduate student of mine named Hartland Snyder, on a problem that almost nobody in physics took seriously at the time. What happens to a massive star when it runs out of fuel and collapses under its own gravity with nothing left to hold it up? Stars spend most of their lives in a kind of standoff. Nuclear fusion in the core generates enormous outward pressure, radiation, and heat, pushing against the crushing inward pull of the star's own gravity. For as long as the fuel lasts, that standoff holds, and the star sits in a stable equilibrium, sometimes for billions of years. But fuel runs out eventually, and when it does, for a sufficiently massive star, there is nothing left in ordinary physics that can stop what happens next. I'd already worked a few years earlier with a student named George Volkoff and my colleague Richard Tolman on the question of what happens to less massive, collapsed stars, objects made almost entirely of densely packed neutrons, held up not by fusion but by a quantum mechanical effect called neutron degeneracy pressure, a kind of resistance that comes from the Pauli exclusion principle itself, the rule that prevents identical particles like neutrons from occupying the same quantum state. We worked out that there's a maximum mass beyond which even this exotic form of pressure can't hold a collapsing star up. Below that mass, you get a stable neutron star, an object almost unimaginably dense, a sun's worth of mass compressed into a sphere perhaps 20 kilometers across. Above it, neutron degeneracy pressure simply isn't strong enough, and the collapse continues. That's where the 1939 paper with Snyder picked up the question: if a star is massive enough that even neutron degeneracy pressure can't stop the collapse, what happens? We worked through the general relativistic mathematics of a collapsing sphere of matter, using Einstein's field equations rather than Newtonian gravity, because at the densities and velocities, Newtonian physics simply stops giving correct answers. And the mathematics led us somewhere I found honestly difficult to fully believe, even as I was deriving it. The star doesn't stop collapsing. From the perspective of someone falling inward with the collapsing matter, the star continues shrinking indefinitely, past any size you'd normally consider physical, compressing toward what the mathematics describes as a single point of essentially infinite density. And somewhere during that collapse, the star's gravity becomes strong enough that not even light can escape from its surface anymore. Around that point, general relativity describes a boundary, we'd later come to call it an event horizon, beyond which nothing, no particle, no signal, no information of any kind can ever climb back out. I want to be honest about something. I didn't fully trust my own conclusion when we finished that paper. The picture it painted was strange enough that I spent real time looking for an error, a place where the mathematics might be misleading us, some physical effect we'd left out that would prevent this endless collapse from actually happening. I never found one. The paper on continued gravitational contraction was published in September of 1939, and I remember being aware, even as we sent it off, that the timing was almost absurd. The same month Germany invaded Poland, the same weeks, the world's attention turned entirely toward a very different kind of catastrophe. A paper describing the theoretical endpoint of stellar collapse landed in a world that had far more immediate collapses to worry about. The scientific community's reaction in the years that followed was not what you might expect for what turned out to be one of the most important predictions in the history of astrophysics. Most physicists, including some whose judgment I respected enormously, treated the result as a mathematical curiosity rather than a description of anything that could actually exist in nature. Einstein himself, in a paper published around the same period, argued against the physical reality of these objects, believing some mechanism must prevent real stars from actually reaching this state. The war came, and my own attention turned entirely toward Los Alamos and the problem of nuclear fission. And I never returned to this specific line of theoretical work with anything like the focus I'd given it in 1939. I died in 1967, and at the time of my death, what we now call black holes were still, for many physicists, a theoretical extreme, rather than an accepted feature of the observable universe. The term black hole itself wasn't even popularized until the physicist John Wheeler used it publicly in 1967, the same year I died. I never actually lived to hear my own theoretical prediction acquire the name most people know it by today. I'm telling you all of this because I want you to understand something before I describe what astronomers eventually found. Decades after I was gone, everything I'm about to describe to you, a star orbiting an object so massive and so compact that its gravity bends the star's path in ways only Einstein's equations can properly capture, is a direct, observable confirmation of the mathematics Snyder and I worked through on paper in 1939, using nothing but pencils, before anyone had the instruments capable of actually detecting an object like this. At the center of our own galaxy, the Milky Way, sits an object called Sagittarius A star, a supermassive black hole with a mass equivalent to roughly 4 million suns, compressed into a region of space that, by cosmic standards, is astonishingly small. Astronomers couldn't observe it directly for most of the 20th century. You can't see a black hole itself, by definition, since no light escapes it. What you can observe with sufficiently precise instruments is the effect its gravity has on everything nearby. And there is quite a lot nearby. Hundreds of stars orbit close to Sagittarius A star, caught in its gravitational grip the way planets orbit our sun, except under conditions of gravity so extreme that ordinary Newtonian orbital mechanics, the same equations that correctly predict the motion of Earth around the sun, start to fail. For most of these stars orbiting at a comfortable distance, Newton's laws still work well enough. But for a small number of stars whose orbits bring them extremely close to the black hole, close enough that the mathematics I worked through with Snyder becomes directly relevant, only Einstein's general relativity gives you the right answer. One of these stars is called S62. Its orbit is so tight and brings it so close to Sagittarius A star at its nearest approach that at that moment in its orbit, astronomers have measured it moving at more than 8% of the speed of light, over 15,000 miles per second, an almost incomprehensible velocity for an object with the mass of an entire star. To put that in perspective, at that speed, the star could cross the distance between the Earth and the Moon in about 16 seconds. I want to walk you through why a star can move this fast without simply being torn apart or flung out of orbit entirely, because the physics here connects directly back to the same equations from that 1939 paper. As an object approaches a sufficiently massive, sufficiently compact source of gravity, general relativity predicts effects that simply don't appear in Newtonian gravity at all. One of these is called frame dragging. The black hole's own rotation actually twists the fabric of space-time around it, dragging nearby space along with its spin. The way a spoon stirred through honey drags the honey around with it, a star orbiting close enough to a rotating black hole doesn't just follow a simple fixed elliptical path the way a planet does around the sun. Its orbit itself precesses rotating slowly over time, an effect general relativity predicts precisely, and Newtonian gravity doesn't predict at all. S62's orbital period is remarkably short for an object at this scale. Its full orbit around Sagittarius A star takes place over a matter of years, rather than the centuries or millennia you might expect for a stellar orbit around a supermassive object. That short period means astronomers studying it can actually watch multiple full orbits within a human research career. Observing directly how the star's path shifts and precesses in exactly the way general relativity predicts, rather than waiting generations for enough data to accumulate. The team responsible for this measurement, led by an astrophysicist named Florian Peisker, working with instruments capable of resolving individual stars at the very center of our galaxy, a region normally obscured by enormous amounts of interstellar dust and gas that block ordinary visible light, used infrared observations to track S62's position with extraordinary precision over an extended period. From those repeated position measurements taken over years, they were able to reconstruct the star's full orbital path and calculate its velocity at every point along that path, including the moment of closest approach to the black hole. When the star's speed peaks at that extraordinary 8% of light speed, I find something genuinely moving in the fact that this measurement exists at all, because it represents the closing of a loop that took the better part of a century to complete. In 1939, Snyder and I worked through mathematics, describing objects so dense that light itself couldn't escape their gravity, using nothing but general relativity and our own confidence that the equations, however strange their implications, were probably telling us something true about nature. We had no way at the time to test that confidence against actual observation. The instruments required to detect an object like Sagittarius A star, let alone to track individual stars whipping around it at a meaningful fraction of the speed of light, didn't exist yet and wouldn't exist for decades. What strikes me most, thinking about this discovery, is how directly it validates a specific quantitative prediction rather than a vague qualitative one. General relativity doesn't just say loosely that gravity near a black hole is very strong. It makes precise, falsifiable predictions about exactly how an orbiting object's path should curve, exactly how much its orbit should precess per revolution, exactly what velocity it should reach at a given distance from the central mass. When astronomers measured S62's actual behavior and compared it against what Einstein's equations predicted for an object with Sagittarius A star's calculated mass, the agreement wasn't approximate. It matched the relativistic prediction with a precision that simply isn't achievable if you're using the wrong underlying theory of gravity. There's a broader star discovered in subsequent observations and catalogued as S4714, whose orbit brings it even closer to the black hole at certain points, an orbit so tight that some analysis suggest it may approach even closer than S62 does, though the measurement carries more uncertainty given how faint and difficult to track a star that deep in the galactic center actually is. Whichever specific star holds the precise record at any given moment, as instruments improve, the broader picture stays the same. There is a population of stars, real objects with real mass, whipping around the compact object at our galaxy's center at velocities that can only be correctly described using the same relativistic framework that predicted in the first place that objects like this compact center could exist at all. I think about what it would have meant to see this data in 1939, sitting in my office at Berkeley with Snyder, checking and rechecking our derivation because the conclusion seemed too strange to trust. We had no observational anchor for what we were describing, only the internal consistency of the mathematics, and a faith which I held more tentatively than people sometimes assume, that nature actually behaves the way sufficiently careful equations say it should, even in regimes no human being had ever directly observed. It would be almost 30 years after our paper before the term black hole even entered common use, and closer to 80 years before astronomers had both the theoretical framework and the instrumental precision to watch an individual star trace out in real time the exact relativistic path our equations predicted objects like this should follow. I never lived to see Sagittarius A star confirmed as a supermassive black hole. I never lived to see the term black hole become part of ordinary language, let alone to see astronomers track individual stars orbiting one closely enough to measure frame dragging directly. What I had in 1939 was a set of equations that led somewhere strange, a colleague willing to work through that strangeness with me rigorously rather than dismissing it, and enough confidence in the underlying mathematics to publish a result I understood most of my colleagues wouldn't immediately accept. That's most of what theoretical physics actually is, in my experience. Whatever the popular image of sudden flashes of insight might suggest, it's slow, careful work with equations that sometimes lead you somewhere you don't expect and can't yet verify, followed by a long wait. Sometimes a wait longer than the physicist doing the original work will personally live to see resolved before instruments and observational techniques finally catch up enough to test whether the mathematics was describing something real. S62, moving at 8% of the speed of light around an object with a mass of 4 million suns, is that resolution. It's the universe confirming, with a precision neither Snyder nor I could have imagined achieving in our lifetimes, that the strange conclusion we reached on paper in 1939 wasn't a mathematical curiosity after all. It was a description of something that actually exists sitting at the center of our own galaxy, still there, still shaping the paths of the stars, unlucky or fortunate enough, depending on how you look at it, to orbit close enough to feel its full relativistic pull. I signed that 1939 paper not knowing whether anyone would ever be able to prove it right. Whatever else history remembers me for, I find a particular kind of satisfaction in knowing that this piece of it, the quiet, careful mathematics about collapsing stars, worked out years before the war, changed the direction of my entire career. Turned out decades later to be exactly as real as the equation said it was.